This is 4.5 work applications. Basically, it's everything we learned in 4.4. You're going to be doing the same exact problems. The only thing that's different is we're going to write these equations now. So when you ask, when am I going to use this? These are actually real life applications where you'll use it. So in this first part of the lesson, you will learn how to solve work problems. Work problems are those that involve the speeds of people and or machines. We'll teach you how to calculate how long it'll take for multiple workers to perform a job together. This lesson is broken down into the following 3 sections: multiple job problems, delayed start work problems, and unknown rate work problems. Now, why do we need to learn about work problems? Well, in order to delve into work problems, it should be understood why it is we study them. The reasons to learn work problems is it demonstrates the need to understand rational expressions and equations and how to solve them. It hones our problem-solving skills and mathematical reason, and it solves real-world time management problems. So let's look at some work basics. If Bridget needs 3 hours to paint a room, how much will she get done in an hour of time? To solve this problem, we will need to divide a single job into parts. So we're basically trying to figure out how many jobs can she get done per hour. So if it takes her 3 hours to paint a room, she gets a third of the job done in 1 hour, another third in the second hour, and in the third hour, another third. So in 3 hours, she gets 1 done. A third plus a third plus a third is 1. Now, if we changed it so that it took 5 hours to do the job, we would see that it would take 1/5 plus 1/5 plus 1/5 plus 1/5 plus 1/5 equals 1. To fully understand this relationship, we should realize that a 3-hour job requires a third of the work to be completed per hour, whereas a 5-hour job demands a fifth of the job to get handled per hour. Using mathematical terms, this relationship is called the reciprocal. So a 7-hour job would translate to 1/7 of the work being completed per hour. Let's look at this another way. To solve work rate problems, it is helpful to use a variant of distance equals rate times time. Specifically, we're going to use Q, where Q stands for the work done, R is the rate of work, and T is the time worked. So let's look at an example. If a machine can produce 2.5 parts per minute, that is the rate. So let me highlight that. So parts per minute, that's a rate, so that's R. I'll put R above that. And 4 minutes, that is time. I'll highlight that in another color. So make that blue. So if I multiply that, the rate is 2.5 or 5 halves. So that would mean it'd be 5 parts every 2 minutes. And if I multiply that by 4 minutes, the units cancel on that, and I get 20 parts over 2. So that would equal 10 parts. So in 4 minutes, it can produce 10 parts. In 40 minutes, I would do 5 halves times 40. 5 halves times 40, that'd be 200 over 2. So that would be 100 parts. And the units would cancel the same. And then if I did 5 halves times 2/5 minutes, that would cancel. The 2's would cancel the 5's. Would be 10 over 10. And that would equal 1 part. Would be complete in that time. Now, if Paul can inventory a small stockroom in 2 hours, that's our time, then his rate of work is what per hour? So a small stockroom, that would be like how much is produced. So that's actually, I'll highlight that another color, that would be Q. So a small stockroom, that would be the number 1. So Q would equal 1, and time would equal 2. So if I use our formula, Q equals R times T. The rate is what we're trying to find. This is 2 for hours, and Q is 1. So if I divide by 2, then R would equal 1/2. It's always that reciprocal, just like we saw before. We just did the basics, so we know that the quantity of items completed is going to equal the work rate times the time. That's the general equation. But now we're going to solve more complex work rate problems. So in most cases, you'll be asked to find out how long it'll take to perform a task if more than one worker does the portion of the task, not just one person. To make these problems easier, we're going to assume that the workers do not get in each other's way, or find a more efficient way to work as partners. So each person is doing their own part. So that's the scenario. They're not getting in each other's way. They're just doing the things together for this equation to work. So we'll talk about different contexts later. So why are we doing this? Well, have you ever heard the expression, many hands make light work? Well, that expression my parents always said when we were cleaning, let's do this together. If we do it together, it's going to be faster. Like if we have to clean the kitchen, if we're all in there working, it's going to be way faster than if just one person's working. So basically, if we work together, we will reduce the amount of time needed to get the job done. So let's look at an example. If Karen works on a puzzle alone, it will take her 7 hours to complete. So as we've seen before, that means her rate's going to be 1/7. It's that reciprocal of how long it takes her to get a job done. So in 1 hour, she'd get 1/7 of that puzzle done. And if Susan took 4 hours to complete a puzzle, then in 1 hour she'd get 1/4 of the puzzle done. So that is her rate. Now, how long will it take them if they're going to work together? So if they're going to work together, the time is going to be the same. We don't know what that time is. How long will it take them to work together? So how long will it take them? What is the total number of puzzles they're going to complete? They're working on one puzzle together, so that's one job. So we know rate times time is the quantity, so that's 1/7 x and 1/4 x. So Karen's portion of the puzzle of her quantity completed would be 1/7 times x. Susan's is going to be 1/4 x, and they're going to complete one total puzzle. So like we saw in the previous chapter, all we need to do is multiply by the LCD. So we can do that by multiplying both sides by 7 and 4. I'll do that in a different color. 7 times 4, 7 times 4. So we get 7 times 4 over 7x. I'm going to distribute that 7 times 4. And then I would get 7 times 4 over 4x. Because remember, this is over 1. That's why you're only doing it to the top number. And 7 times 4, that's 28. So the 7s would cancel and I get 4x. The 4s would cancel and I would get 7x equals 28. I add these two together and I get, what would that be? 11x equals 28. And I'm going to divide 11 on both sides. And so x is going to equal 28 over 11. Let me type what that is. 28 divided by 11 is going to be 2.54. So we could say that's going to be about 2.5 hours. So 2.5 hours, that's going to be about 2 hours and 30 minutes. Let's look at another example. Paul can complete an inventory in 2 hours. Aaliyah can complete the same inventory in 3 hours. If they work together, how long will it take them to complete 3 inventories? So we've got Paul, and we've got Aaliyah. Okay. And so Paul's rate would be, he'd get a half job done every hour if it takes him 2 hours to complete one. And Aaliyah would get a third job done every hour if it takes her 3 hours to get a job done. So they work together. There's no delayed start. The time starts at the same, so that would be x for both of them. So the quantity completed would be 1/2 x and 1/3 x. So we want to figure out, okay, well, what is the total number of inventories we're taking? So inventories. So let's say we're doing 3 sets of inventories. That would be 3 then. So Paul's portion would be 1/2 x. Aaliyah's portion would be 1/3 x. And the total number of inventories are 3. So just like before, we multiply through by the LCD. In case this is 2 and 3, you can multiply by 2 and 3 on both sides, or you can multiply 3 by 6. But last time I did it by both numbers, this time we'll do it by 6. So if we distribute, that'd be 6 over 2x plus 6 over 3x equals 18. So that would be 3x plus 2x equals 18. We would then get 5x equals 18. We divide by 5 on both sides. So that would be x equals 18 over 5 hours. So let me get my little handy dandy typey calculator thingy majig here. And that would be 3.6 hours. So x would equal 3.6 hours. We know how to do dimensional analysis. We can give a better answer than that. We could say that, well, that's 3 hours. Well, how many minutes? Well, 0.6 hours, if we want to convert that to minutes, we put 1 hour on the bottom and 60 minutes on top. 0.6 times 60. Well, let me show you. I could change 0.6 as the same thing as 6/10. So 10 goes into 10 once. 10 goes into 66 times. So 6 times 6 is 36. So a better answer than 3.6 hours, something that we'd actually say would be 3 hours and 36 minutes. Do I have to answer it this way, Ms. Urquhart? I would accept 3.6 hours. That's fine. But you'll really impress me and put me in a good mood if you can do it this way, because this is a challenge. I want to make sure you still know how to do dimensional analysis from those earlier sections. And dimensional analysis will be on your test. So even if you don't put it in here, there's still any questions about dimensional analysis when it comes to your unit test. All right, let's look at this example. Lito's department can deliver enough parts to fill a storeroom in 8 hours. Jessica's department uses the part to build another product. Her department can deplete a full storeroom in 12 hours. Starting with an empty storeroom, how long will it take Lito's area to fill the storeroom while Jessica's department is working? All right, so here's Lito. And then we have Jessica. And it's Lito's department. Let's say department. Sorry, that's horrible. Jessica's department. Just trust me that says department. All right, so we already know the rate of Lito's is going to be 1/8. And Jessica's is negative. The word deplete is a negative notation, so that'd be negative 1/12. So the times are the same. So this would be 1/8 x, negative 1/12 x. And the total number of storerooms, oh, they only mentioned one, so that is going to be 1 here. The total number of storerooms. So the equation then becomes 1/8 x minus 1/12 x equals 1. If you need a review of how to find the LCD, we've got 8 and 12. It goes 8, 16, 8 times 3 is 24. 12 goes up by 12, 24. Oh, there's our LCD. So if you multiply by 8 and 12, it'll still work. It's just this will be a little bit easier. So I'm going to multiply through by 24. So it'll be 24 over 8x minus 24 over 12x equals 24. 24 over 8 is 3x. 24 over 12 is 2x. This equals 24. So 3x minus 2x is x. So that would be a total of 24 hours. And that would be our solution. Let's look at a follow-up question. How would the example above change if the storeroom were half full when both departments started working? Well, that would just change the total number of storerooms to a half. Well, that would probably just be 12 then. Well, let's check that. So if we did 1/8 x minus 1/12 x, and instead of 1 we use 1/2, well, I'd still multiply by 24 as my LCD because 2 goes into 24. That would be 3x again minus 2x because that wouldn't change. And 24 over 2 is 12. And 3x minus 2x is x. Yep, pretty obvious, right? You could probably have guessed that one without doing it. But you can just see how it's important to know how full a storeroom is. It might be a half, it could be 2 storerooms. So this changes based on how many jobs you're trying to complete, how many full parts. All right, let's look at a delayed start work problem. Derek owns a pool and wants to fill it. His hose will take 15 hours to fill the pool. His neighbor's hose will take 12 hours to fill the pool. If Derek starts to fill his pool with his hose and then 2 hours later uses his neighbor's hose, how long will it take him to fill the pool? All right, so we've got Derek's hose. We've got his neighbor's hose. And the rate for Derek will be 1/15. 1/15 of the pool will be filled every hour, so the rate would be 1/15. And if it takes 12 hours for his neighbor's hose to fill the pool, 1/12 of the pool will be filled every hour. So the time is not the same. So he is going to be using, so like if we had them the same, they'd both be x. But the way I like to think about it is which one is going longer. So if he starts to fill with his hose and then uses his neighbor's, that means his hose has been going for 2 hours longer than his neighbor's. So his should be 2 hours more than his neighbor's. So we multiply this, so this would be 1/15 x plus 2. And then this would be 1/12 x. Now, we are just filling his pool, so the number of pools would just be 1. So let's set up this equation. So it'd be x plus 2 over 15 plus x over 12 equals 1. So 12 and 15, let's think about that. Well, I know 15 can be broken up into 3 times 5, and 12 can be broken up into 3 times 4. So if we use that jealous neighbors example that I did before, if you don't know what that is, just ask me, I'll go over it again. The LCD, we would need a 3, a 4, and a 5. So that would be 4 times 5 is 20, so 3 times 20. So let's multiply through by 60. So if I distribute this, I would get 60 times x plus 2 over 15 plus 60x over 12 equals 60. Now 60 and 15. 15 goes into itself once, and 15 goes into 60 4 times. So we have 4 times the quantity x plus 2. 12 goes into itself once, and 12 goes into 65 times, so that'd be 5x equals 60. I'm going to distribute the 4, so I get 4x plus 8 plus 5x equals 60. I combine these like terms, so I get 9x plus 8 equals 60. I subtract 8, I get 9x equals 52. Divide by 9. X is going to then equal, let's see, about 5.8 hours. And if we wanted to be more accurate, that would be x would equal 5 hours, and then we would do 0.8 hours times 60. And so that would be 48 minutes. 5 hours and 48 minutes if we wanted to be more accurate. But 5.8 hours works as well. All right, let's take this same similar problem, but let's say we have 3 hoses instead of just 2. So if we more than 2 people type problem, in this case it's more than 2 hoses, but if there's more than 1, we just add another line and we do the same exact thing. So a garden hose can fill a swimming pool in 15 hours. So we have the garden hose. I'm just going to do GH for that. A larger hose can fill it in 10 hours, so that's 1/10. And the fire hose Wow, that would be a fast one. Can do that in 6 hours. So all of the time are the same. They didn't say they started later or anything. So in our case, this is still all the same. So this would be 1/15 x, 1/10 x, and 1/6 x. And the number of pools we're filling, we just want to fill one. They didn't say anything different. There's only one pictured here, so I'm going to say 1. So I would get 1/15 x, or just x over 15, plus 1/10 x plus 1/6 x equals 1. So we want to see what all these go into. So we've got 15, 10, and 6. 6 would be 6, 12, 18. 10 doesn't go in any of those. 24, 30. Let's see. 10 would go 10, 20, 30. Ooh, that's good. 15 would go 15, 30. There is our LCD of 30. I'm going to use the green. So I'm going to multiply through by 30 on each side. So 30 over 15x plus 30 over 10x plus 30 over 6x equals 30. 30 over 15 is 2x. 30 over 10 is 3x. And 30 over 6 is 5x equals 30. I add these up. 2 plus 3 is 5. 5 plus 5 is 10. 10x equals 30. Ooh, this is a nice one. X would equal 3 hours, right on the nose. So we don't have to do any dimensional analysis on that. Alrighty. This is just like the previous one, just an extra line. Alright, last one. Unknown work problems. Alright, there's a situation when a worker's individual work time is unknown. This video will demonstrate how to solve for that work rate when a person works with someone else to complete a job. So let's look at this example, okay? So here's our example. It takes Tom 4 hours to build a fence. If he hires Jack to help him, together they can do the same job in 3 hours. If Jack built the same fence alone, how long would it take him? So let's look at this. We got 2 people. We've got Tom, we got Jack. Well, we already know that if it takes him 4 hours to build a fence, then in 1 hour he'd get 1/4 of the fence done. If it takes Jack X amount of hours to complete a job, he would get 1 over X of the job done in an hour. Well, we know we want to complete 1 fence, number of fences. They completed 1 together. They took 3 hours when they were working together, so we can plug that in. And so this would be 3/4, 3 over x, and then we have our equation. So just to review, it takes Jack X amount of hours to complete a job, so his work rate would be 1 over x. So the combined one is that hours that they work together to complete 1 job. So we've got, back on track, we've got our equation is going to be 3/4 plus 3 over x equals 1. Now we haven't had x on the bottom, but it works the same way. We're going to multiply both sides by those denominators, 4 and x, 4 and x, and we're going to distribute. So we have 4x times 3 is 12x over 4. 4x times 3 is also 12x, and then we have x on the bottom, and 1 times 4 is 4x. So 12 over 4 is 3, so that'd be 3x. These x's cancel, I get plus 12, and I get 4x. Subtract 3x, subtract 3x. Ooh, there's another nice one. X would equal 12. So that means, let's go back to our table. This is 12. How long would it take Jack to build the same one alone? Would be 12 hours. Because remember, it's that reciprocal of 1 over x. All right, and that's it. Now, if you have any questions, feel free to ask. This is nothing really new. It's just how to set up the equation. You really want to write out that rate, time, quantity, completed table. It's going to make your life so much easier.